particle P1 of mass m is dropped from a point A. So let's say here's A, here's B. Alright, so this particle P1, which has a mass of m, it's dropped, pen's not going to work, dropped, so it's going in this direction and it falls towards point B. At the instance when it's dropped, a second particle P2 is projected upwards from B. So here's particle P2 and it's going in that direction. Alright, so it's projected towards A. Alright, with an initial velocity equal to, so here with an initial velocity equal in magnitude to twice the terminal velocity of P1. So we have this one with a velocity, initial velocity twice. Now I can see that the terminal velocity is going to be g on k, so I'm going to write two lots of g on k's there, just have it ready. But I can see that I have to show that first. Each particle experiences a resistance of mkv as it moves. Alright. So if we look first at our particle 1 here and write an equation for it, so our acceleration, we can see that gravity will be going in the direction of motion, but we've got a resistance of mkv, so because the mass is m, so I'm dividing by m, I just get minus kv there. Now it says show that the terminal velocity is that. Alright, so remember the terminal velocity occurs when the acceleration is 0, so let's make the acceleration 0 and we can see g will be kv, and we can see, sorry, I should put vt there we go. So vt is going to be g on k, which is what we're looking for. So that is the terminal velocity. That's all nice and fine. Whoops, shouldn't have written that out. Alright, so then show that the time taken for particle P2 to reach velocity just v is that. So we're looking for our acceleration equation in terms of v and t. So we're going to put v to t for this one. Alright, so what's our x double dot in this case? So gravity is going in the opposite direction to motion, and we've also got a resistance of mkv, so kv when we divide through by the m. Alright, so just rewrite that. So our time, and I'll call this particle 2, so I'll call it time 2. So I need to put everything upside down and put a minus at the front. There we go. And you can see I'm going to need a k on top, so I'm going to put a k on top, which means I need a 1 on k out the front. And also, velocity wise, this is going up, so it's going from the initial velocity, which we know is 2g on k, up to some velocity v in that time. Alright, so let's forget about the minus, not forget about it, but let's switch the limits around. So we're going to have, the pen doesn't want to work at all, so we're going to have log g plus kv, and between v and 2g on k, there we go. So that is 1 on k, and we're going to have log. Alright, so putting the 2g on k in, you can see we're going to get g plus 2g, which is 3g. And putting velocity in, we're going to get g plus kv. Alright, which is what we wanted to show, so we're all good there. Alright, so suppose the particles collide at an instant when P1 has reached 30% of its terminal velocity. So when this velocity is 30% of its terminal velocity, which we know is the g on k, and we're looking for a velocity equation. So we really want time and velocity here. Right, so let's go to our P1 equation. Just give this a little room over here. I'll do P1 in green. So P1, we're going from a velocity of 0 to a velocity, because it's falling to of 0.3 g on k, or 0.3 times its terminal velocity. So let's remember that its acceleration equation was g minus kv. So if we use v to t, we are going to get g minus kv there. So within the time, let's put a, sorry, I should have done it slower. So if I tip everything upside down, I need a minus k, therefore I divide it by a minus k. So I've got minus 1 and k at the front. All right, and remember our velocity, we are going from 0 up to 0.3 of that terminal velocity, which is g on k. Okay, so what do we get? We get, if again, I'll change the limits around, so we're going to get log of our g minus kv, and our limits are going to be just the other way around. And remember, that's the same as g on k. So we get 1 on k log, all right, subbing in 0, we'll just get g. Subbing in 0.3 g on k here, remember the k's get cancelled, so 1 minus 0.3, lots of g's, is 0.7, lots of g's. And the g's will cancel. So 1 on 0.7 is the same as 1 divided by 7 on 10, which is the same as 10 on 7. So we are going to get, if I just lift this a little bit, 1 on k log 10 on 7. All right, so that's at what time the collision occurs. And remember the time at a particular velocity for the other particle. So if I make this t1, and we can see in blue the t2. So clearly if they're started at the same time and they collide, they must collide at the same time. Therefore, these two times must be equal. All right, so let's set them to each other. Let's just set them to each other. So 1 on k, they're both log. So what are we really saying? We're saying 3g on g plus kv has to be equal to 10 on 7. All right, so we're going to get 21 g's. Yeah, 21 g's is 10 g's plus 10 kv's. So we've got 11 g's is 10 kv. So we've got, there we go. So V would be, I'll make V the subject, 11g divided by that 10k, and that'll be in meters per second. All right, so that was just making the times equal to each other, which is, yay, that's what we wanted to show.